There is an invisible shield wrapped around this planet that you have never seen, never touched, and almost certainly never think about. It stretches tens of thousands of miles into space. It deflects a continuous stream of charged particles blasting out of the sun at 1,000,000 miles per hour. It has been protecting life on Earth for billions of years. And right now, according to data collected by satellites, ground observatories, and the most detailed geomagnetic models ever produced, it is weakening, shifting, and accelerating in ways that the scientists who study it most closely did not predict even a decade ago. The European Space Agency's swarm satellites have confirmed that Earth's magnetic field is losing strength at approximately 5% per decade, a rate 10 times faster than scientists previously estimated. The magnetic North Pole has moved more than 600 miles in the past century and is currently racing towards Siberia at roughly 34 miles per year, more than 3 times the speed it was traveling a century ago. A region of dramatic magnetic weakness southwest of Africa has grown by nearly half the size of continental Europe in just 11 years, and it is now weakening faster in some places than at any time in recorded measurement history. And in late 2023, something happened deep inside the Earth that scientists have a name for, a name that captures the suddenness of the event: a geomagnetic jerk. The planet's magnetic field did not just continue its slow drift, it lurched, and every system that depends on that field, navigation, aviation, satellites, power grids, and the migration patterns of thousands of animal species, is now operating in a world where the ground rules of geomagnetism are being rewritten faster than anyone expected. To understand why this matters and what is actually happening, you have to understand what the magnetic field is and where it comes from. The Earth is not a simple ball of solid rock. At its center is a solid inner core, roughly the size of the Moon, made primarily of iron and nickel under such enormous pressure that it remains solid despite temperatures exceeding 5,000 degrees Celsius, hotter than the surface of the Sun. Surrounding that solid inner core is a liquid outer core approximately 9,400 miles thick, churning in slow, complex convection currents driven by heat escaping from the deep interior. This liquid iron, conducting electricity as it moves, behaves like the coil of wire in a generator. As it circulates, it generates electric currents, and those currents produce a magnetic field that extends far out into space. The self-sustaining system is called the geodynamo, and it is the engine behind the magnetic field that shields this planet. But the geodynamo is not a stable machine. The liquid outer core is turbulent, irregular, and constantly changing. Regions of intense upwelling compete with regions of downwelling. Patches of reversed magnetic flux, areas where the field lines plunge back into the core rather than emerging from it, the opposite of the global pattern, form, drift, grow, and dissipate over decades and centuries. Every change in the dynamics of that liquid iron manifests with a delay of years to decades as a change in the magnetic field at Earth's surface and in space above it. The magnetic North Pole, the point where a compass needle points, is not the same as the geographic North Pole, which marks Earth's rotational axis and sits permanently at 90 degrees north latitude. The magnetic North Pole is a dynamic feature, determined by where the geodynamo's global field configuration happens to be strongest in the northern hemisphere at any given moment. For most of recorded history, it sat in the Canadian Arctic. Explorers first precisely located it in 1831 in what is now the Nunavut territory of Canada. For roughly a century after that first precise measurement, it drifted slowly, a few miles per year, mostly within the Canadian Arctic. Then something changed in the liquid core beneath, and the drift began to accelerate. By the late 20th century, the pole was moving at about 10 miles per year. By the early 2000s, it had accelerated to roughly 25 miles per year. Today, it is moving at approximately 34 miles per year, having already crossed into the Arctic Ocean, and heading in a direction that, if current trends continue, will take it towards Siberia within decades. The World Magnetic Model, the official global reference used by the U.S. Federal Aviation Administration, the Department of Defense, NATO, the International Hydrographic Organization, and civilian GPS systems worldwide, was updated in December 2024, the new WWM 2025 release, specifically to account for these changes. Without recalibrating navigation systems against the updated model, a flight attempting to travel 5,280 miles from South Africa to the United Kingdom in a perfectly straight line using the previous model would arrive 93 miles off course. The South Atlantic anomaly is the most dramatic physical feature of the current magnetic field changes, and it is where the most alarming recent data has emerged. The anomaly is a vast region of dramatically weakened magnetic field strength, centered over South America and extending across the southern Atlantic Ocean. Inside this anomaly, the total field strength is approximately 1/3 of what it is near the magnetic poles. The weakened field provides less shielding against energetic charged particles from the sun and from cosmic rays, which means that satellites, spacecraft, and the International Space Station passing through the anomaly are exposed to significantly elevated radiation levels. NASA routinely powers down sensitive instruments on spacecraft when they pass through the South Atlantic anomaly to prevent radiation damage. The ISS, whose orbit takes it through the anomaly on every pass, has documented elevated radiation exposure during transits. Satellites operating in low Earth orbit have reported more frequent electronic upsets, unexpected resets, data errors, and hardware anomalies when crossing through the anomaly than at any other point in their orbits. After analyzing 11 years of continuous magnetic field data from ESA's Swarm satellite constellation, researchers published findings in the journal Physics of the Earth and Planetary Interiors in 2025, showing that the South Atlantic anomaly has expanded by nearly half the size of continental Europe since 2014. That is an enormous geographic expansion of the weakest region of Earth's magnetic shield in just over a decade. But the finding that most concerned the research team came from a subset of that data focused on the African side of the anomaly. Since 2020, an area of the South Atlantic southwest of Africa has been experiencing magnetic weakening at a rate significantly faster than the rest of the anomaly. Lead author Chris Finlay, professor of geomagnetism at the Technical University of Denmark, described the finding by saying, "The South Atlantic anomaly is not just a single block. It is changing differently toward Africa than near South America, and that there is something special happening in this region causing the field to weaken in a more intense way. The minimum field strength at the anomaly's center dropped by approximately 30 nanoteslas in a single year, a decline consistent with the long-term trend, but striking in scale for a 12-month period. Scientists link this intensified weakening to features at the boundary between Earth's liquid outer core and its solid mantle, specifically what they call reverse flux patches, regions where the magnetic field lines plunge back into the core rather than emerging outward. These reverse flux patches represent disruptions in the normal global pattern of the geodynamo and their behavior at the core. Mantle boundary appears to be driving the accelerated surface weakening above the South Atlantic. The geomagnetic jerk that occurred between late 2023 and early 2024 is a separate and deeply significant event. A geomagnetic jerk is precisely what the name suggests, a sudden, sharp change in the rate of acceleration of the magnetic field, visible across a broad geographic region. The 2025 State of the Geomagnetic Field report, compiled from satellite observations and data from approximately 160 ground-based magnetic observatories worldwide, confirmed this jerk and described the field entering what it called a more active and uneven phase. Geomagnetic jerks have been recorded historically, but the mechanisms driving them are poorly understood. The leading hypothesis connects them to waves of acceleration moving through the liquid outer core, rapid fluid motions that propagate upward to the core mantle, boundary, and produce sudden changes in the field detected at the surface. The 2023-2024 jerk follows similar events recorded in 1969, 1978, 1991, 1999, 2003, 2014, and 2017. Their increasing frequency in recent decades may be significant, but scientists are careful to note that the historical record is incomplete, and that apparent frequency increases can reflect improved measurement resolution, as much as actual changes in core dynamics. The rate at which the overall field is weakening has become a central concern. ESA's Swarm mission data, as reported by Scientific American, confirmed that previous estimates placed the weakening rate at roughly 5% per century. The actual measured rate from satellite data is 5% per decade, 10 times faster. This difference is not a minor calibration adjustment. It changes the timeline for every projection built on the old estimate. Historically, scientists had suggested that a complete magnetic pole reversal, an event where geographic magnetic north and south physically swap locations, might be thousands of years away. The revised weakening rate, if it continues, suggests that timeline may be considerably shorter. Dr. Catherine Constable of the Scripps Institution of Oceanography has been careful to note, as have other leading geomagnetists, that the current weakening does not constitute clear evidence that a reversal is imminent. Studies published in Nature in 2024 confirmed that while the field is moving and weakening, there is no immediate sign of a reversal underway. When reversals have occurred in the geological past, they have taken thousands of years to complete. During these transitions, the field does not simply vanish. It becomes more complex, with multiple regional poles appearing simultaneously in different locations around the planet. Life survived every reversal in Earth's history, as paleomagnetic records confirm. But the technological civilization that currently exists on this planet did not exist during any previous reversal, and its vulnerability to a substantially weakened or reorganized magnetic field is a genuinely open question. The solar dimension of the current magnetic field story is impossible to separate from the internal changes. Earth's magnetic field does not respond only to what is happening inside the planet. It interacts continuously with the solar wind, the constant outflow of charged particles from the sun, and with the much more violent eruptions of solar flares and coronal mass ejections. A study published in Nature in April 2024 confirmed a direct correlation between high solar activity and short-term magnetic field fluctuations, with GPS systems and communications networks experiencing sudden blackouts and interruptions during peak solar storms. The period from 2023 to 2025 produced a series of strong to severe geomagnetic storms, including an extreme G5 event in May 2024, the most powerful geomagnetic storm to hit Earth since the Halloween storms of 2003. During the October 2024 G4 storm, magnetic observatories in Greenland recorded declination deviations of up to 16.7 degrees, a measurement that describes how far a compass needle deflected from its expected position during the storm. These are not theoretical values. They are direct readings from instruments. A declination deviation of that magnitude exceeds the operational margins of navigation systems that rely on magnetic heading. Aircraft, ships, and precision survey equipment operating during these events had to compensate for a temporary magnetic environment that the models they normally rely on had not anticipated. The response from governments and scientific institutions has been significant. The U.S. Department of Homeland Security issued new guidelines in March 2025, recommending that critical infrastructure operators prepare for potential magnetic field-related disruptions. Research grants were awarded in 2024 to develop new sensor networks and early warning systems for geomagnetic anomalies and space weather events. Emergency management agencies in Brazil and South Africa, the countries most directly beneath the South Atlantic anomaly, began running preparedness drills specifically focused on sudden power or communications outages linked to magnetic disturbances. The International Association of Geomagnetism and Aeronomy regularly updates the world magnetic model precisely because the field is changing fast enough that a static model becomes navigationally dangerous within just a few years. The December 2024 update introduced, for the first time, a high-resolution version of the model called WMM-HR 2025, offering navigational accuracy at a spatial resolution of approximately 300 kilometers rather than the previous 3,300 kilometers, an 11-fold improvement in spatial precision designed specifically to cope with the accelerating complexity of the field's behavior. The biological dimension of this story is perhaps the most underappreciated consequence of what the data is showing. Hundreds of animal species rely on Earth's magnetic field as a navigational compass. Migratory birds use it to maintain heading during long-distance seasonal migrations. Sea turtles use it to navigate from feeding grounds to nesting beaches thousands of miles away, sometimes returning to the exact beach where they were born after decades at sea. Salmon use magnetic field cues to navigate from the open ocean back to the specific rivers and streams where they hatched. Sharks, rays, whales, and dolphins have all demonstrated magnetoreception, the biological ability to detect and navigate using magnetic field information. Research published in Science Advances in 2023 documented disoriented migratory birds in Brazil, where the South Atlantic anomaly has caused the greatest surface-level magnetic weakening. Studies in animal migration in 2024 linked shifting magnetic field patterns to measurable changes in the migration routes of species across the South Atlantic region. As the anomaly continues to expand and the global field continues its accelerating shift, the navigational environment that these species evolved over millions of years to read is being rewritten beneath them. A NASA-led study published in June 2025 added one more layer to the picture that makes the current moment feel particularly significant. Analyzing paleomagnetic records stretching back more than 500 million years, the study found that Earth's magnetic field strength has risen and fallen in synchrony with atmospheric oxygen levels over geological time. When the field was weak, oxygen levels tended to be lower. When the field was strong, oxygen was more abundant. The proposed mechanism connects a strong magnetic shield to reduced loss of atmospheric particles to space. A strong field deflects the solar wind that would otherwise strip the upper atmosphere of lightweight oxygen molecules over geological time. His does not mean that the current field weakening poses an immediate threat to atmospheric oxygen levels. These are processes that operate over millions of years, not human lifespans, but it places the current changes in a larger context that makes the magnetic field's behavior relevant not just to navigation systems and satellite operations, but to the deepest questions about what sustains the conditions for life on this planet at all. The scientists studying these changes are careful with their language. They describe a field that is behaving unusually, accelerating faster than models built on the historical record predicted, and entering a phase of greater activity and complexity. They do not use the word crisis. They do not predict catastrophe, but they also do not pretend that everything is normal. The 2025 State of the Geomagnetic Field report written in the careful language of official science, nonetheless concluded that the data confirm a field that is shifting, accelerating, weakening in key regions, and responding strongly to solar activity. ESA's Swarm Mission Manager, Anja Strome, said that the satellites are providing a big picture of a dynamic Earth, and expressed hope that the satellite data record can be extended beyond 2030, when an approaching solar minimum will allow new insights into the planet's interior. The instruments are working. The data is coming in, and what the data is saying, consistently and across multiple independent measurement systems, is that the invisible shield wrapped around this planet is not behaving the way science predicted it would. How far the changes go and what they ultimately mean for the technology and the life that depends on this field is a question that the planet itself is in the process of answering, one measurement at a time.